Hello, my name is Rob Grzywinski. I'm going to go through a presentation that I gave to the University of Potsdam at their Knowledge Representation and Reasoning group. Talk a little bit about myself first. I've been a Silicon Valley CTO for the past 30 years. I've been a part of startups as long as I can remember. And what's interesting is I still write my own software. Of my group of peers, I think I'm the only one left who still writes their own software. And given all of the exciting and fun things that are happening right now in AI and Gen AI, it's a great place to be. My background's actually in physics, math and physics, but I spent most of my academic career writing software, so it felt like the right thing to do, especially because the internet started to become a thing. And where my focus is throughout this whole time is thinking about how to make software not a problem. And the way that I think about it is as a constraint problem. When I gave this presentation at the University of Potsdam, I had to try to think about what was the most useful and interesting thing that I can give that academic group. So this is going to be kind of an overview of all of the different things that I've been thinking about and working on in this area. Specifically, this is the group that has created or shepherded answer set programming. If you've never heard of it and so forth, hopefully you'll look it up on Wikipedia. But I'm going to talk about how in the world did I get to ASP from the problem that I was working on. So one of the interesting things about being a CTO in a software company is that my job is mostly about translating. It's from translating the needs of the business to technology and then translating the needs and constraints of technology back to the business. And this has been what I've done for the past 30 years. So you learn some different techniques for how to do that translation, what works well for different groups and so forth. And what's always been interesting to me, especially on the software side of things, is that developers look at the problem of software as itself. As I always say, if you give somebody a box, you define the box that they're in, they will fill that box. Whether or not it's the right box or whatever, it almost doesn't matter. Folks will fill the box that they're given. So when you give somebody a problem like writing software, they make that the problem. And if there's one thing that I've always not done myself is I've never taken the box that I've been given. I always try to see what other ways can you represent that information in different ways. So when I think about software, when I think about the lines of code that I'm writing, I always try to think about what are the other possible ways and the different other manifestations and machinations of the software that I could write at any one time. Even as simple as writing a print statement. What are the different ways that I could write it, given the different things that I could do? And then I always think about why. Why am I choosing a particular piece of or technique or whatever that I'm doing within software? And where I managed to distill all this down to is the underlying problem is actually a constraint problem. And it's a problem about discovering what those constraints are, whether those are the functional requirements coming from product, the non-functional requirements that come from the software and the software team itself. And I would love to give a talk on this whole idea about how do things like code reviews, how is that nothing more than uncovering and communicating constraints that exist? Why is your code, if your company has a particular coding style, it's less about why is it that coding style, more so than the fact that your code needs to look like that. So those are constraints that are applied to your code. And so again, as somebody who's been doing this for a couple of decades now, I was trying to distill down what this core essential idea was. What are these constraints? And more importantly, like just how can I write them down? If I want to think about them or reason about them, if I want to articulate them, I need a way to do that, to do just that. I need a way to articulate these constraints. If I think that software is a constraint problem, what are the constraints? It seems like a kind of obvious thing. And another thing that I alluded to a moment ago, which is given a set of constraints, what are all the different possible solutions? Meaning, what are the lines of code that are valid, that can be written, that solve that same problem, but potentially using different lines of code? And just to say that it's constraints all the way down. So even when you think about the syntax of the language itself, those are constraints. So if you use like a C style language like Java, JavaScript, etc., C sharp, there's certain ways you can write things. It's for, open paren, variable, etc. You can't put, for equals, or you can't put for and a brace. And again, those are constraints. So even at the lowest level, from the ideas and the fact that something can't be both black and white at the same time, otherwise it's gray, and that's not black and white. It is either one or the other. You go all the way down to the actual lines of code itself, or the actual symbols in the code itself. And those things are constrained. And if you look at all of those, even if you look at the idea of the fact that I look at Python on one side and say JavaScript on the other side, those are two different sets of constraints that I can take the exact same problem, say bubble sort, and I write it in Python, and I take bubble sort and I write the exact same thing in JavaScript. They will look completely different. They will be different lines of code. Even though the problem domain is exactly the same, the constraints that each language applies, again, all the way down to the symbol layer, define what that solution looks like. And so I'm going to keep going over this theme and so forth. And I'm not expecting you to buy into this idea yet, but my talk is going to come in and suppose that is true. So my ask for now is just put on the hat of saying, hey, software is a constraint problem. I have to think about everything, every step that I'm doing, what constraints are such that the solution is what it is. Again, when you're looking at a piece of software, what are the ideas? What are the constraints that made it look like it is? So back during COVID, when we all had a whole bunch of extra time on our hands, I went and I tried to figure out, can I find a way to articulate these constraints? So I went through a whole bunch of formal methods. If you've ever heard of Talos or ISTAR, which I think only 4 people on the planet have ever heard of, I was going down all of these different techniques, business process modeling and UML, and some things that are more mainstream. And it was interesting because I kept landing on Prolog, which is a declarative logic programming language. And a lot of ideas like Talos and ISTAR, both of them kind of manifested themselves in this thing called ConceptNet, or Concept Base, sorry. And so I spent a lot of time just reading and understanding and learning Prolog. And what's interesting about Prolog, if you've ever spent any amount of time with it, is that you have your problem that you're thinking about, like writing down a constraint of some nature, which is the problems I was working on. You have Prolog, the language itself, so you have to understand the syntax and so forth. And what's annoying about Prolog is that you have to literally know how it's going to be executed. And there's these things called cuts and things like that help you walk the trees, that is the space of things that you're working on. And so long story short was I started off with this problem of how do I represent these constraints? I ended up going to Prolog. So I ended up spending months learning Prolog. And then you have this other problem of every time you try to do something in Prolog, you have to think about how the Prolog execution environment will execute on the code. And it was this mad mess of just like, I had this problem, but now I have this problem and I have this problem. And it was just the cognitive overload, which is another common theme that I'm going to keep talking about. A lot of the things that we as humans do, whether it's in software or any job that we do, is we're really looking to try to manage the cognitive load. How many things do you have to stick in your brain, and how complicated are they, and how close are they to the ideas that you want? You know, I can take the idea of a red ball and represent it with a number 1. And that kind of simplifies, if you will, the idea of red ball number 1, and maybe a green triangle is number 2. And now I can, every time I see a red ball, I just have to remember 1 and 2. And maybe that simplifies things, but you also have to remember that the 2 equal each other. And maybe if you do that enough times, it becomes muscle memory and you don't have to remember it. And again, all I'm trying to get at here is like, if trying to remember 50 different objects, it might be easier for me to represent them as a string of numbers, for example. And that's one way of managing cognitive load. And the same thing is true with software. If you look at a massive code base, the reason we have things like object-oriented programming and things like that is a way to draw a box around a piece of code and say the only way you can enter or exit information from it are through these very specific methods that have these protections associated with them. And again, that's how we do cognitive load management. So, again, as I was going through this problem of manifesting, articulating these constraints, I ended up with this prologue problem and this prologue execution problem. And I was like, well, how do I manage this cognitive load? Like I had this problem and I'm trying to it was a mess. So I'm like, there has to be another language that just allows me to talk about the constraints without worrying about the way that it's executed and things like that. So there was a glimmer of an idea, but I didn't find it. And I finally found this thing called ASP, which is answer set programming. It's not very well known. It's the standard problem if you've ever done research on a topic that you have these disparate graphs of things and there's just one node, one edge that connects these two nodes together. And once you've found that edge and you know how to now walk between them, you can kind of put these things together. But what's interesting is until you can find that edge that connects the two nodes, it's impossible to try to find these different groups. So it was nearly impossible for me to find ASP. And one of the reasons why I gave a talk at the KAR group at Potsdam is to give them more knowledge. So perhaps we can draw some more parallels between these two things. So once I found ASP, I really fell in love with its simplicity. Sure, its syntax has a whole bunch of turds associated with it, which are a pain in of itself, but I didn't have to remember this middle part that I had to do with Prolog, which is trying to figure out how it's executed. ASP is extremely straightforward. The execution model is extremely straightforward once you understand it, how it works. Like you don't have to think about it anymore. It separates the what from the how. So I can, which is literally just that. I can write down statements and I don't have to think about how they're executed. I just know what it is and it gives me the answer. And I can always work both backward and forward. Whereas again, with Prolog, there's just so many different machinations in the middle to deal with. And as I gave an example earlier, anytime that you can take a program, an idea, and simplify it. So again, we could write software in assembly, but it's hard once you get beyond a certain amount, the cognitive load of trying to get your concepts mapped into assembly is really hard. So we started to create other languages on top of that. And as we moved up the stack, you can now think of concepts like a car, and a car has wheels, and those are kind of standard examples rather than remembering these individual instructions. And I think ASP has a very similar idea of that. I can abstract my concepts away and I can talk about their individual concepts rather than thinking about specifics about how the language works or how it's executed and so forth. So ASP is really interesting, especially because it thinks about things like combinatorics and search spaces. These are things that I'm more than happy to give additional talks on if there's folks that have questions on these things. But one of the things that you spend a lot of time doing as a software engineer is writing unit tests. And unit tests are a combinatoric problem. So what are combinatoric? So if you think about all the different ways that you can write the numbers 1, 2, 3, you can write it 1, 2, 3, 1, 3, 2, 3, 2, 1, etc. You can think of all the combinations of those things. And those are the combinatorics. And that's in fact, that's a search space problem. You're defining the search space of all of the possible combinations. And that's what writing unit tests are, is every time you're writing a unit test, you have all this possible search space of all the possible ways that the program can be run. And as a programmer, you're looking to you don't want to write every single one of those tests. You want to write a test such that it takes care of all these cases. Like if you test this one thing, it tests all of these cases. If you do this, you do this. And what's interesting, again, from a concept standpoint is we already have these concepts of combinatorics and search spaces and so forth in unit tests. And the fact that ASPs first and foremost thinks about things in terms of combinatorics and search spaces and so forth. I'll just admit to the groups that have never seen ASP, this stuff probably seems very ethereal. This talk was obviously designed to give to people who are intimately familiar with ASP. So I apologize. I can give another talk on the very details of that. I'm going to go through some examples so you can kind of see them. But the goal of this is, again, to give you a much broader oversight of how ASP kind of fits into a bigger picture. So once I had this ASP thing, and once I had a way to now materialize constraints, now I had to actually pick a problem that I wanted to do this on. Because just because I have a new chef's knife in my kitchen, I need to figure out a new dish that I want to try to make. So I was trying to think of that. So what I did is I came up with a couple of examples, which I'm going to take you through now. These are all available on this website that I created called Surface Tension, specifically in this blueprint section. I'm going to give a couple of these examples. There's a whole bunch of them here. I tried to go through all of the things as a developer, as a leader, as a CTO, we're trying to go through. Like, how do I think about software? How do I think about these constraints? So if you've ever used the Google Firestore or Firebase product, I'm going to talk a little bit in the weeds right now for a quick moment to just give you an idea of what this technology is. But the way that I write my products, because I want to think about the problem that I'm solving rather than the technology that's implementing it, is I tend to use as many managed services as possible. And Google provides Firestore, which is a NoSQL database, so think Redis or something like that, but fully managed. I don't have to do anything. It scales to billions and trillions of documents. I don't have to scale it up. I don't have to scale it down. They charge me per write, per read kind of stuff. The economics make absolute sense to the problems that I work on. So super simple solution to me. But the next step that you have, as with any technology that you have, is you have to learn its constraints, right? So the way that Firestore works, which again is a NoSQL database, is that it has a set of rules that you can apply so that certain users with certain conditions can run certain queries. So you're always doing two different things simultaneously in Firestore. You're trying to remember the security and the rules that you have to write, and you're trying to write these queries that satisfy the data needs that you have. So if I want to print, for example, this list of things here, I would create a document potentially for each one of these things, and then I would want to query all of the documents that are there. But you can imagine a permission model that sits on top of that where only certain users with certain permission can do that. So you write rules that provide that ensure the fact that no one can ever read the data unless they have certain constraints. And then the queries are such that you ensure that you get the data such a way that maps to those rules such that the data is protected. So to use this technology as a developer, I have to constantly keep both of these constraints in my head. I have to keep the rules constraints, I have to keep the query constraints in my head. And so as a developer, the first thing you do is you find a document like this, which is like, how do those queries get written in there? And you see a section like all the different query operators that you have available. There's limitations for each of those queries that if you have a not equals query, that you can't combine it with not in and not equal. And I'll just scroll down to the bottom here. You can see all of the different types of limitations that you have. There's an interesting case where you have to break the query down into disjunctive normal form, DNF form, and then you can only have at most 30 disjunctions. So now again, just imagine this thing where some business person says, well, we want to create a website that has these records here and they have such and such a constraints. And those are one set of business constraints. Now on the other side, you're like, well, I'm a developer. I have to use this technology and the technology has its constraints. So what are those constraints? So you just picture this world of all of these constraints that you have. Again, the business constraints, the Firestore rules, the Firestore queries, and you have to somehow jam all this stuff in your brain and it all has to fit. And again, they're extreme minutia of these details. So in this case, again, I'm trying to think about which users can access which documents. And in this case, I have to actually take that. So accessing data in users and in information is one query. That query, I have to manifest what that query is with some ands and ors in my brain. And then I have to turn that into disjunctive normal form. And then I have to ensure the fact that there's no more than 30 clauses within that thing. So again, you think about if you don't do development and you're like a layman when it comes to this on the business side or something else, you don't realize, well, why does software take so long to write? And the problem is like, it's these things. I can't just write this query because I have to worry about the security constraints. I have to worry about these other things. And when I write this query, if it breaks, I have to understand, well, what caused it to break? What were the constraints such that that's not the sufficient code for that? And I have to do all that. And again, I'm normally doing all this in my brain. And now that I had this notion of ASP, this language that allowed me to express these constraints, I did the next obvious thing that one would do. And I kind of go through this exposition in this article again. I'll just say that these are all publicly available. You can go in. Um, but I went in and I did the thing that you would expect to do. So as you remember at the top of this document here, just zip up to the top really quickly, it tells you what all these query operators are. So these are all the possible operators. So I write this down. I just simply state these facts, which is what they're called in ASP. And if you're, again, I come from spending a bunch of time writing Prolog and also thinking about relational databases. So the way that you conceptualize these things is you think of these things as relations. So I'm basically relating this symbol to these words. And so if you think about this as a database table or an Excel table, I'm basically doing a mapping between not equals in this. And so when I wanted to manage my own cognitive load, so I'll literally put you into the editor that we have for these things. One of the ways to show this is what the answer set looks like, which is in ASP, the things that pop out, answer set programming is you're trying to get out answers of these combinations of elements. And so in this case, the combination of all of these statements put together, this is the result. And when you look at this is, there's too much to grok here. Your brain doesn't do it. So we came up with visualizations that sit on top of this, such that when you look at this, this makes a lot more sense. I can see that this is mapped to this and et cetera. You can go through this. And I wanted to create an environment in which rather than just writing code in a text file, I wanted to give all of my ideas that I was having and put them in one place. And I wanted them to look visually appealing so I could visually separate them, again, to help me reduce cognitive load. So this is all a rich text editor. So like this is all editable. You don't have to go into Markdown and then convert that to rich text. Like it's 2025 here, people. You can actually write it in rich text editor. So all these things are in here. And we actually put ASP, there's different that's a language, and there's different interpreters or solvers, as they're called in ASP. And we embedded one of those solvers in here. So literally this web page that you're looking at has a solver built into it, such that the solution of this problem is this thing. So it'll make a little bit more sense as I go through here. But again, I just want to point out that this is all live information. You can see when I click on this, it says that this code block is the code block that is currently being used by this. And I can do things. So if you think about a SQL query, for example, I could do a select, basically, in this case, the operator versus the textual description. So basically select the operator from this and return it for me. And I can get this in this thing, which is basically what this says. Again, I can create a whole separate talk if you're interested in what this language means. But basically what this is saying is query this out. You don't care what's in this space and put it into this other thing. I'll just say, if you're super interested, the arity, the number of arguments in one of these relations is important. So notice that I can have an operator or an atom, as they're called, with an arity of 1, which has one argument, and an arity of 2, and they're two different things. Again, just to say, I went through every one of these things, every one of these operators, everything that is in this file, every one of these constraints, limitations, and so forth. And I went through every single one of them. Like, for example, I wrote down that the not equals operators, again, just to create reduce cognitive load. So we have this new notion of the fact that there's this atom called not equals, and it represents these two things. And then I can go through here and apply different constraints to this. So every where clause must have an operator that's valid. And what's amazing and beautiful about ASP compared to some other similar languages is what is called elaboration tolerant. And that means that you can add new concepts or remove concepts from it without having to redo the whole thing. You can elaborate on it without making much change to the rest of it, or really any change. So I really wanted to exploit this, because what you would typically do in an ASP program is you would write it, you would comment out a line, and you would run the program. And if it worked, you knew one thing. And if you uncommented out that line and ran it again, you knew another thing. So rather than doing that, I wanted to create an environment in which I can look at those two things together. So in this case, notice this is green and this isn't. And if I click on this, this is green and this is not. So I'm able to take all of these different statements above it and run it with this and see this result, and run it with this and see another result. Again, this will make a lot more sense if you know ASP, or if you want me to go through it, I can go through in detail. But again, the main point is that we have an editor in which we can incrementally build up all these ideas. So just as you would read through this and you would jam it in your brain and go, okay, I know the operators are this. I know these rules are that. And I can just add these things on top of each other and I can walk through. And then again, at every one of these steps, I can run all these tests and I can say, well, if I put, in this case, let's see, there's no operator literally called not equal. So if I specify a where clause with a thing that doesn't exist, it says that this program, this is ASP's way of saying like, no, that's not something that exists. So I can tell you all those. And I can also put out different error messages. So for example, I don't know if I give this example. Yeah, so in this case, it says like this is not a known query, or these are not known operators and things like that. So I can actually give different types of results of these things back out. So again, not to spend too much time on this, but the point is I went through every single one of these things and I wrote unit tests for every one of these different operators, every one of these different approaches. If you remember that whole thing I talked about with the DNF, the disjunctive normal form, that ends up being a way that you operate on these structures such that you reduce the tree down to a certain form. And so taking this query, which you can always put a domain-specific language on top of this to make this easier to write. Again, you could just imagine a world in which you take a query from, you just literally take this line of code. You can easily write something that translates this directly into ASP and then tells you an answer. So you never have to work in this form, but just to say like this, you can just picture this query where this query has an and then each of those ands have different clauses that sit on top of them. And this is the tree view of that. And again, just to show you that these are just answer sets to this ASP code. And in this case, we put a different visualizer on top of it so that the tree is obvious. But the point is that once I translate this thing into this, I can determine whether or not, in this case, there can only be one array contains clause per one of these disjunctions. And in this case, you can see that there's one here and one here. And once it puts it into the DNF form, you can see that this then isn't something that this program supports. So what's interesting again is I can encode all these constraints, I can unit test all these constraints, and then I can actually ask questions of these things by giving it different programs, different different manifested forms of the queries that I'm doing, and I can see what are the problems with these things. And again, just to walk through this really quickly, you can see every one of these constraints that are there. So what's interesting about all of this is that I was able to take a document, an English natural language document like this thing, and codify it such that now I can actually ask questions of it. I can actually get results from this without having to memorize this whole thing. I've reduced this whole cognitive load from this. I'm going to walk you through two more quick examples of things that I encoded with this. Another thing that I did, one of the things that you run into when you're writing software are things like if you run in a multi-threaded environment, or even if you run on multiple servers, you have producers and consumers. A producer can produce things at a certain rate, a consumer can consume them at certain rates. And you want to see, given a buffer that exists between them of a certain length, you want to ever see if you get in a state in which a producer can't produce anymore, a consumer can't consume, such that they get in a deadlock condition. And typically there are languages that are used. TLA Plus, for example, was written by Leslie Lamport, who just interestingly enough just retired in January of 2025 from Microsoft. I was hoping to have reached out to him to talk about some of this stuff. Unfortunately, he retired. So I've got to reach out to the group community in general, and I'm yelling out to the crowd. Hopefully somebody knows somebody who would be interested in this. But typically these are problems, and I linked to, this is a YouTube video about somebody who actually had one of these producer-consumer problems, and they were looking to see without, like it's really hard to prove whether or not your software will deadlock or will starve, or if you have a race condition. And there are languages like TLA Plus that you can actually prove. And they're used by companies like Microsoft and Amazon when you do like consensus, in Redis, in order to make sure that all of the different shards are up to date, use a consensus approach like Paxos, and Paxos was written by Leslie Lamport, and it was proven to be correct in specifically in TLA plus. And so what I wanted to do is take, again, problems that we have in programming and see if I can encode them in ASP. And I can give a whole other talk on this. I think I took a very novel approach that I honestly don't believe has ever been taken before, which is to turn it into a traditional planning problem, which takes different actions and sees the results on the states. And to prove that, again, think of it as a combinatoric search space problem. Take all possible actions that all producers and consumers do and run through every single one of those possible combinations and see if any of them result in a deadlock. And what I was able to show, so for example, producers produce and they get into these notify states and so forth. And these are, again, just to point out, this is live in here. So for example, this shows three particular deadlock conditions. I can actually say, what's great about having a constraint language is you can define the constraint that defines a deadlock. So you can actually say, and let me show you that because it's actually kind of interesting. Do I have it here? So basically a deadlock is the state in which both consumers and producers are in a state of waiting. So a producer is waiting for a consumer to consume and a consumer is waiting for a producer to produce. And if you get to that state, that's a deadlock. So you're actually able to write these things out. I can say that there's a state at which sometime instant I that all producers and consumers are waiting, that's a deadlock condition. And again, just to walk you up here a little bit, there's different actions that are performed based on the state of the queue at a certain time and blah, blah, blah. There's not actually that code. If you look at the size of the scroll bar here, like there's not that much code. And as you can see, most of it is me writing unit tests to ensure the fact that these things work the way they do. So this is maybe 30 or 40 lines of ASP that have been individual incrementally through elaboration tolerance unit tested and so forth. So, and that's one of the problems of languages like TLA plus and even like Lean, which is another theorem proving kind of language, is that it's really hard to test. You're just given this block of code and you had this problem of producers and consumers, and you look at this block of code and now there's this other problem, which is like, well, how do I make sure that the program that I wrote actually represents my problem and is correct? And what's been amazing about using ASP is I can incrementally, as my developer brain tells me, I can unit test every one of these steps to prove to myself that these things are correct. And again, long story short here, I was able to actually take a known scenario where if you look at this second argument is the time step. So at instant 0, 1, 2, 3, 4, producer 2 produces, producer 2 produces, etc. You can kind of see, we can walk through this again in a different example. You can see it visually here. And it actually gets to a state in which all of both producers and consumers are all waiting, such that you end up with a deadlock condition. So again, in this video that I referred to at the top, this somebody goes through a really nice presentation about how he found this deadlock using TLA plus. And I was able to test my program by writing all these conditions out, taking his scenario, showing that it deadlocks. But I can also show, which is not a thing easily done in TLA plus, but it can be done, is I can actually show every possible set of states that would lead to a deadlock condition. In this case, there's actually 16 total of them, but I can run them and I can show you all possible states. So as you saw just how quickly that was, some of these problems are actually very quick to solve. But I can show you all possible deadlock scenarios given, I don't know what the particular case is, given a single consumer, 2 producers, a buffer of 1, I can actually show you all of the possible states that the system can get in. And, this is, you can show starvation, you can show deadlock and so forth. So, and again, we did it in such a way that it's once you get used to these things, you can see that at state 1, a producer produces, that moves, that puts, it went from the buffer was originally empty to now I produce something such that the buffer is full. And then now that the producer keeps producing. Anyway, you can walk through all these steps. But and what's even more is we can add some visualization here such that you hover on each state and it would show you the 2 states. And you can then see, and what's more, and what's interesting, and I could talk about this for hours, but you can actually write things on top of these constraint problems that look at the solutions, and you can look at how the solutions are similar and how they're different. Which is absolutely fascinating to be able to do. Oh, and because this is in a rich text editor and everything else, like I can literally just hit undo And we can walk back to my original state, which is, again, what's amazing about these programs. Oh, go back another step. Sorry, I changed to the state. Great. So now we're back to where we were with 3 results. So, just here to show this is a case where producer 1 starts and then producer 2. In this case, is producer 2 starts and 1. And what's great by looking at the combinatorics, by looking at all the possible solutions, you actually get insight into the set of cases such that this happens. Anyway, the point that I'm trying to represent here is something that would normally only be represented in a language like TLA plus, a prover, a solver, etc. We're able to incrementally write the code in a logical way in using primitives that make sense. If the buffer is not empty and somebody consumes, like, is that action allowed, et cetera. And we're able to represent this space. We're able to go through it, and we're able to show that this program either works or doesn't work and the things that we can do to fix it. So in one case, we looked at how it can help developers do development. In this case, we helped show how that you can actually get into the nitty gritty and show how a running execution program is running. And again, I think I did something really novel here, which is to represent this as an AI planning problem. And then finally, I did an interactive fiction example. I grew up in the 70s and 80s, and my parents always bought me these choose your own adventure books so that you would go like, do you want to slay the dragon? Go to page 4, and then you'd go to page 4 and you go, oh, you died. It's like, okay, I don't want to slay the dragon. These things come from interactive fiction, which think of games like Zork and so forth. Love these things. So to me, these things are world building. Look at a different set of actions that I can do and things that occur in that world. I can build things like rooms and ogres, and I can have them inhabit this space, and I can perform actions. I can take a drink of water, I can close a door, I can pick up an axe. And to me, these things are just nothing more than constraint problems. Like, what rooms can and can't I go into? If I have too many things in my inventory, can or I cannot pick them up? I can represent all these things as constraints. So I wanted to encode a world building problem because to me, fundamentally, when you look at software, I'm building a new world. Every time I build an interface, like this interface, for example, I'm building a new world in which you can inhabit. And the inhabitants of that world have certain rules they can and can't follow. And to me, that's a constraint problem. So I took the canonical, if you've ever spent any time in software and interactive fiction, you know about the cloak of darkness. It's a really interesting problem that Roger Firth wrote. I've got it linked here. I do say you look into it, but it's what everyone uses when they're testing out their interactive fiction programming languages. And so I did the obvious thing, which is I programmed this whole thing in here. I did things like when the character moves, that means that if they're at a location, they move a certain direction, and that is an allowed direction, then that's something that they can do. Again, the language is a little esoteric, and I can, of course, walk you through it. But the point is I can also build up this incrementally. I can say how moving works. I can provide output from these things so that, in this case, if I go north from the foyer, one of the things that's part of the cloak of darkness is that this is what's output once you try to go north from here. So I can do those things here. So if I try to move east from the foyer, it says that there doesn't appear to be an exit to the east. And I don't want to claim that you would ever want to write an executable program in ASP and run it. But the point here is that I can take basically anything. I can go from Firestore rules to thinking about producers and consumers to world building. And I can represent all of them, which to me represent all of the facets of software development. I can represent them in one language. And what's more is I believe that this different way of slicing these worlds, so again, from the software itself, you can actually encode the grammar of a language. I did the crazy thing, and I actually wrote I wrote the constraints that are ASP in ASP. So for example, you can only have, like, this is what the language looks like, right? It's basically, I'm saying that the direction from the foyer north leads me back to the foyer. And this is a rule or a statement. And I can write this constraint in here. I can't put like an equal sign in here. This is not something that I can do. So I wrote those constraints. So not only, as I said earlier, that the language itself provides a set of constraints, I was able to encode those constraints in ASP. So not only things like Firestore rules, not only like the execution of multi-threaded server producer consumer world building, but I can actually do the language itself and I can apply all of these constraints. And what I hope that you starting to see by my saying that software is a constraint problem, that there's there's a set of solutions that will that are valid given all those constraints. So you can imagine a world in which I can just generate that program, for example. So I don't want to get too far in the weeds here, but again, the goal of all this is just to simply show that I can take the entire cloak of darkness in this thing, and I can run through a set of things where on the first step I drop the cloak and then I move north and then I move west, and you can see the state as it changes and what are the different outputs that happen at those things. And because this is a planning problem, and because ASP is a search space thing, I can actually run through every possible solution of my thing. And I'll admit that there are a few people that use ASP in game programming, specifically when they're designing puzzle games, to make sure that there are solutions to their puzzles and there are not other solutions to puzzles. And so in this exact same way, I can do this. I can make sure that there's never a case where the ogre gets stuck in a closet somewhere because of something, because I can literally search the entire space and do that. And because ASP has a solver on top of it, it can actually do these NP hard problems and actually reduce that problem set down and so forth. So just wanted to walk you through all of these possible types of things with ASP. So I went through all of the different ways that I think about how ASP can be used. And I went through the different ways in which I think these are different problems that are all have the exact same face. Notice I was able to, again, go from world building through the actual software itself to a producer consumer problem to that. And again, just to point out that I've gone through a bunch of different examples here, including going through music. To just quickly touch on this, that if you've ever spent any time in music, building up chords, relative minors and scales and things like that, those are constraint problems. You're literally applying a formula that takes you from a set of notes to other notes. And I took that exact same world and I did things like build up chords. So and what's interesting about ASP, just as in that example where I showed you I had an operator with an arity of 2 and I could say, give me the operators. I can do the same thing and I can say, give me all the inversions of a C major chord with like A in the root position. What are all the other possible inversions that I can go through? And again, you can have it do that. Because to me, again, I think of these things as constraint problems. So again, this was really directed towards the ASP group, the KOR group at the University of Potsdam. But I just want to say they look at this problem. They spend their time working on graph problems and doing the traveling salesman problem. They work on all these NP hard problems. But I believe, as I've just shown, that ASP can be used in a much broader sense, a much bigger picture as to the things that are possible to do with ASP. And I think that given the complexities that we all have as developers and the changes in those constraints that occur, and just the challenge of discovering those constraints, if we had ways of talking about them better, cheaper, faster, then we would end up with better, cheaper, faster software. So what's interesting is if you spent any time on the reasoning side of LLMs, I'm going to kind of switch over to Gen AI for a quick second here. If you've listened to Terence Tao and so forth, one of the ways that mathematicians are kind of moving the state of the art forward using LLMs is they'll encode a math problem in a language called Lean, which is a math-like language that's provable. You can put it through a solver and it can go through each step and ensure that each step is correct. And so you write a math problem in Lean and then you can allow the machine to do that. One of the problems with doing that is it's just really hard to go from math problem to the encoding in Lean and basically back and forth between that. And people are using LLMs to not only help generate additional steps in those proofs, but help encode from their brain to Lean and so forth. People are talking about languages like TLA plus in terms of proving that the software that gets put out by these machines is provably correct. But as I think I've just shown, hopefully, that you see that there's ASP covers a much broader range of things that you could possibly do. And so, and I've shown that you can incrementally, through elaboration tolerance, develop these codes. So it's not like lean where it's like one shot and you're looking at this thing and you're trying to understand it, or TLA plus, which is this big program and you're just like, it's math and you're trying to wrap your head around it and you can't prove whether it's right or not. And if you get a wrong answer, is it wrong because the program's wrong, or is it wrong because the problems are wrong? And again, through elaboration tolerance of ASP, you end up in this really interesting space where you can unit test every single step of the way. And I think that's so important because it takes some of those challenges that you have with those other two languages and it translates them into something much more approachable. And again, into a much broader set of topics, as again, I think hopefully that I've shown. So I think that ASP has a huge opportunity to do things. Um, and let me move on to the next step here. And this can be a little bit mind-blowing, but let me just do this here. So one of the things I started doing was taking ASP programs. Again, I mentioned earlier that I said that I wrote ASP in ASP such that ASP itself, the language, I provided all the constraints. And given that, then I can elaborate all of the possible combinations, every possible ASP program. So I can give it some constraints and I can say, I only want up to 5 different atoms. I want only 3 rules. I constrain the problem. And then I can literally write every single possible, every program that could ever be written with those constraints. I can output that. And it's pretty mind blowing when you see the world in that way. I looking at humans are really bad at combinatorics. I could give, let me see if I can find this really quickly. Hopefully I can. Um, I did an example of file systems. And one of the interesting things is looking at trees. So if I say that I have 2 folders and 2 files, and I look at every possible combination of tree that can be represented in that way, it's every possible combination of those trees is a much larger set than you think in your brain. Again, human brains are not good at exponentials, which are combinatorics. They're definitely not good at factorials and things like that. Like the spaces just blow up really quickly. So what's interesting, just to say, like when you say that you're going to generate every possible program, you think about if I have n atoms, they can be written in n ways. Like you're just doing, n times m times o times p times q times r, and you just have this massive space. So it's just interesting to elaborate every possible one. You end up with terabytes of data, and it was just interesting to go through them all. Anyway, I can generate a program, and then I can basically tell an LLM, I can give it some prompts, and I can say, hey, basically these set of instructions for how you translate these ASP things into language. So I can say, I can take this statement, which is basically constraint. Well, I can just read this. It says that it cannot be that there is no evidence, so not E. It can't be that I don't have an E and I have an A, a C, and a D. So that's what this rule says, is again, if I if I don't have an E, I can't also have these types of things. And again, I can translate this here. If there's evidence, there is evidence of C, D, and E if there's no evidence of B, and I always have A. And so again, I can take this program, I can hand it to an LLM with a little bit of prompting, and I can have it do this basically 100% of the time, all the time. Then what I can do is I can give it a set of domains, and I can just pick anything from paper to writing to culinary to software to programming to anything, just like all the possible domains. And this is where LLMs are great, is they can just come up with some super interesting ideas and just give you ideas. And then what I say is basically take these and come up with things that these things represent. So in this case, what is E? Like, what is this? And E is in fact parsley. So in the world of culinary, so cooking, come up with a bunch of different things that these atoms represent, and then take this program translation and put these things in there. So as before, we said that there is evidence of A, which means that there is always A. And then in this case, it translated that into there is rosemary. It cannot be that there is no rosemary, but there is oregano, this and this. So you can start to see once you have the machine kind of like write this out for you in natural language, it starts to make a little bit more sense. When I read this before, is that it cannot be that there is no evidence of E, but there is evidence of blah, blah, blah. When you read it this way, it cannot be that there's no rosemary, but there is oregano, basil, and parsley. It's like, oh, I start to get it. And then I went one step further, which is once you take this, you can say, give me a scenario that exactly represents this. And so I'll read this to you just really quickly, just so you can hear it. You can obviously read it on the screen. But again, given this program through the domain of culinary, it came up with the statement, you're the head chef at a bustling restaurant. You prepare your signature dish that absolutely requires a dash of rosemary. So what you notice is that it has to use the statement that whatever is a must always be in there. So it translated that into you're preparing your signature dish that absolutely requires a dash of rosemary, which is readily available in your pantry. However, if you run out of time, you have the option to substitute it with either oregano, basil, or parsley. So what this says is if there's no B, then there can either be C, D, or E. So that's what this says here. So if there's no time, which is B, it is that you can have either one of those in those dish. But remember, a successful dish cannot exist without parsley while simultaneously having these three things. So in other words, if you had these three things, it cannot be that you don't have this also. So that's what it says. So what's fascinating about that is this direction is uninteresting, but think about it the other way. Now, I just generated this, right? I took this program, I went through these steps, I have a scenario. Now I can go the other way. I can give this to an LLM and have it fine-tune this. So I can take all of these as the input and say these are the output. I'll let that sink in for a moment. I can take a program and I can have it generate a scenario, and then I can flip that over and I can take that scenario and have the LLM learn that when it sees scenarios like these, that this is the ASP that it needs to spit out. So this is a super fascinating way. And again, remember, I can generate effectively an infinite number of these, and the LLM can generate these. Sure, you have to prune the bad examples, and there's lots of interesting cases, but I actually learned more about the knowledge representation problem, which is what this is. It's an interesting problem to take knowledge and try to represent it as code. So this was the way that I thought about it, is take programs that you know work, translate them into things, use the LLM to translate them into things that are statements, and then flip that and then use that as training data. Let me go even one step further. So I already ran this, but just to say this whole environment here is integrated with LLMs. The LLMs, the way we set up this IDE, so to speak, this integrated development environment, is everything above the cursor, the LLM can see. Everything below the cursor, they can't see. So it allows you to kind of jump in between and get different ideas. So what I can do here is I can talk to one of my LLMs, which I've set up as charms. We could talk about all this if anyone's interested. And in this case, what this says is from the answer sets, we can get all possible ingredients and turn those into statements. So what I did is I actually ran this program. So when you run this program, its answer is these are the only combinations that meet the requirements of these things. And I can have this turn it into it because it already knows that A is rosemary and B and E is thyme, et cetera, parsley. And so it can write this out. It can look at this answer set and it can turn this stuff into language. So again, the goal here is I can take this scenario, fine tune it such that these come out. So I can give it scenarios and it can spit out ASP. And then once you run it through ASP and you get out solutions, you can take those solutions and clearly turn them back into natural language. And LLMs are really suited to do this. But what's interesting is ASP does more than that. As I mentioned earlier, I can make statements about these things. So just as I showed you with the queries with Firestore rules, I can say, given this query, is it valid? So in this case, I can say, can I make a signature dish out of rosemary, oregano? Can I make my signature dish out of rosemary, oregano, and basil? And obviously, I can have the LLM translate this into this program. I can run this program, and this is the way that ASP says that something doesn't happen. And in this case, I can go into this in really long-winded way, but it suffices to say that you can write ASP that helps you debug ASP. So I can actually write an ASP program that helps me understand why an ASP program doesn't work. So the way you debug an ASP is you just simply look for the rules that contradict what you say. And so I can do that. So I can actually write ASP that says that the reason why this program doesn't work is because of a certain rule. So again, imagine now you're in a world where you can ask a question, and one of the problems with LLMs today is they can't really tell you why. But now we can actually generate all of this data. So not only can I generate this scenario that goes from this program to this, turn it around and fine tune it, once I have this, I can actually run all of the other things on top of it. I can run, again, I can enumerate every one of these and I can enumerate every possible input, and then I can get all of the outputs in natural language. So I can literally say, can I create my signature just out of blah, blah, blah? And then you, behind the scenes, you put that out, and then the LLM returns an answer through debugging that says, no, you can't write this because you said that it must include oregano, for example, or it cannot be, this is true. So again, now I have these pairs where I can take a logical statement. Through ASP and generating data, I can write all of the possible English statements and there are whys as to what happens. Then I can use that data as training data for the next set of LLMs that I'm building. So this seems to be a wonderfully provable, interesting approach to generating data. And again, I can go through every possible combination of dish that I want to create. And I can even in an elaboration tolerant way, I can go through and say like, sage is known to change the flavor of the dish, and I don't want that. So I can make the statement that if, I forget what F was. Oh, sage is F, sorry. F is a new thing to my environment. I say that it cannot be that you combine sage with oregano, and it cannot be that you combine sage with basil. And now I've added those things. So again, I can change my statements. I can generate all this stuff. I can come back and say, this is what happens. Again, LLMs don't have a lot of data that says, well, what if the world changes and what are the next step and what are the repercussions of that world changing? And now, again, we can generate all this data. If I add something to my environment, I can run those programs. I can say why they're not valid. And again, I can use this as a way to provide training data to LLMs. And again, I can do this in the full combinatoric space, which is a little bit mind-blowing. So, and again, you can ask questions the other way and say, hey, I want to create my signature dish and I want to use oregano. So what else can I put? What are the other possible sets of ingredients? And I can do that. And again, I can go back and say, why is that true? Which set of rules cause that to be true? So this is just a super long-winded way of saying, like, we can use ASP for all of this type of stuff. Again, this is not saying that ASP is built into the LLM. You're using ASP to generate all this new training data that's potentially very rich while having the whys and whats and wheres, and use that in the next stage of LLM training. So this was my call to action to the KRR group, and just say, hey, I think, again, ASP is perfectly positioned to really reach its arms into every aspect of these things. Now, again, I don't believe that human beings are going to sit there and write ASP programs. I think through what I've just shown earlier, that we can fine tune these things or even make the next generation of models if the model builders know, if the Anthropic and the OpenAIs and the Googles of the world know that this is something that we want. We can say, hey, load it up with gobs of this data, and then imagine ASP as a tool use on this thing such that you can have it would translate what you're saying into a set of logic statements behind the scenes, run that as part of a tool chain, and come back with a result that has provability to it. You can imagine the applicability in legal and in healthcare and like all of these cases where you have all of these really rich constraints. And again, even encoding these constraints can be done as we get the models better, as they learn how to take human statements and turn them into programs. We can go further, and you can build, again, tools to help you prove whether or not these programs are right or not. I think there's a ton of opportunities there. And again, if any of you listening to this are in academia and are interested in writing papers, I would love to be part of that with you. If any of these ideas really wet your whistle, I just want my name somewhere on it so that it makes me, because I have to deal with the validity of the statements that I make. And everyone always asks me, well, what papers are you published in? So like, I need my name on them, but I don't need to be top author. Like, you guys take this and run with it. There's so many things to do, even just simply taking these set of use cases that I've built and turning them into papers. Simply sitting with just taking a producer-consumer problem and looking at that as a planning problem is a whole paper in and of itself. And just to say, hey, by the way, I realize that not everyone knows ASP. So of course, because I'm crazy, I wrote a whole set of tutorials that takes you through how to start with ASP, how to think about it. And you can just literally go through these set of tutorials that I've put on this website for you. And to go even further, because I am one crazy SOB, if you're familiar with Charm, every one of these pages that you go into, you have the ability to talk to these things and say, hey, like, can you give me and so if again, if you're a charm user and you have your charms that you like to use, you can use them. Every one of these documents you can use as reference material is what you see here. And you can have a buddy as you're going through every one of these tutorials. Like you don't need, of course, reach out to people if you need them, but like you don't need our help. Like you can use now these agents with these things and say like, hey, um, I'm a bit confused about how ASP rules are written. And you can just talk to this thing and it can help you work through these things, etc. And you can add all of these different tutorials and you can work through these examples and you can go through here. So like we're in a very different world than we were just a few short years ago. Your LLMs are with you everywhere you go, and they can help you learn all this stuff. Again, last call to action here is there's so many places where ASP can go that other languages had no opportunity to go. Let's make this part of a thing and let's go big. As much as I hate putting my email out on the internet, come find me. It's more important to me that you guys find me. And if you're interested or you have ideas, if you're just starting your undergrad or master's program and you need a research topic, like these ideas of taking and combining traditional symbolic logic, which is where ASP fits, and combining it with planning problems for things like robots and whatnot that you would normally traditionally think of that. But you can think of other problems as planning problems. Even the writing of software statements can be thought of as a planning problem. The modification of programs as you go from program A to program B and add a constraint, you can model that as a planning problem and enumerate all those possible sets. Again, come reach out to me and I would love to hear from you. I hope you found this useful. Put some thoughts and feedback in the comments. I'd love to do more of these talks or I'd love to deep dive where you have questions.